Far out in the cold reaches of our solar system, almost 1 billion miles from the sun, there hangs a small world the colour of a candle flame seen through fog. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. This little world is called Titan, and it is the largest moon of Saturn. Tonight, we are going to wander across it together, slowly, in no hurry at all. If you could float in space above Titan and look down, you would see something that does not quite look like a moon. You would see a soft orange sphere, smooth and hazy with no sharp edges. The surface is hidden. A thick blanket of air wraps the whole world in a warm, dusty glow. From a distance, Titan looks more like a tiny planet than a moon. It looks like a small, glowing pumpkin drifting in the dark. Saturn floats nearby, enormous and pale, ringed with bands of ice and dust. Titan moves around it in a slow, patient circle, taking about 16 of our days to finish one trip. The sun from way out here is small. It looks like a bright star rather than a fiery disk. Daylight on Titan is dim and golden, like the last hour before sunset on a hazy afternoon at home. It is always a little like dusk. Now picture this. Beneath that thick orange haze there are lakes, there are rivers, there are clouds that gather and let loose a slow, gentle rain. There are seas wide enough that you could not see across them. There are shorelines and bays, and even places that look a lot like river deltas back on Earth. The strange and wonderful thing, the thing that makes Titan one of the most curious places we know, is that none of that liquid is water. The lakes on Titan are made of methane and ethane. On Earth, methane is the gas we burn in stoves, and ethane is its close cousin. They are gases at room temperature here, but Titan is so cold, around -290 degrees Fahrenheit at the surface, that these gases become liquids. They flow, they pool. They evaporate, rise into the sky, form clouds and fall again as rain. Titan has a weather cycle just like Earth does, but the rain is not water. The rain is fuel. This is the open question we will sit with tonight. What is it really like on the surface of a world where the seas are not water and the rocks are not stone? How does a place like that work? How did it become what it is? And could anything, in any form we might recognize or fail to recognize, be alive in those dark, cold lakes? We do not yet know the answers. We have visited Titan only a few times, with one small probe that touched down years ago, and one larger spacecraft that flew past again and again before its mission ended. We have radar maps that show us the shapes of the seas. We have a few photographs from the surface, dim and strange, showing rounded pebbles of ice in a flat orange light. But most of Titan remains a mystery. Most of its weather, most of its chemistry, most of its history is still waiting to be understood. There are theories about how the lakes formed. Some scientists think the basins were carved out by flowing liquids over long ages, the way rivers carve canyons on Earth. Others think the basins may have collapsed from below, like sinkholes opening in soft ground. Both ideas have evidence. Neither one is fully settled. There are theories, too, about what lies beneath Titan's icy crust. Some researchers wonder if there is a deep ocean of liquid water hidden far below, kept warm by the moon's slow inner heat. If that ocean exists, it would be one of the largest bodies of water in the solar system, and it would be a quiet, dark place we have never seen. The evidence is suggestive. It is not yet proof. So tonight, let your thoughts drift outward, past the bright inner planets, past the asteroid belt, past Jupiter, all the way to the pale gold haze that hangs around a small moon in orbit around a giant ringed world. Settle in, get comfortable. We are going to spend the next few hours wandering across Titan very slowly, looking at its rivers and its dunes and its strange weather, and wondering together what kind of place it truly is. Let us begin with the simple shape of the thing. Titan is a moon. It orbits Saturn, the ringed planet that sits far out in the cold middle of our solar system. If you have ever seen a picture of Saturn with its bright bands of rings tilted in space, then you have seen the world that Titan circles. Titan is one of dozens of moons in that family, but it is by far the largest. It is so large, in fact, that it would not look out of place among the planets themselves. To get a feel for its size, picture our own moon in the night sky. Now imagine a moon nearly half again as wide. Titan is bigger than the planet Mercury. It is the second largest moon in the entire solar system, beaten only by Ganymede, which orbits Jupiter. If Titan were free of Saturn and drifting on its own around the Sun, we would almost certainly call it a planet. Its diameter is about 3,200 miles across, roughly the distance from New York to Los Angeles, end to end. Yet for all its size, Titan is far away. Saturn sits nearly 10 times farther from the Sun than Earth does. Sunlight that takes 8 minutes to reach us takes more than an hour to reach Titan. By the time that light arrives, it has thinned and weakened. Noon on Titan is dimmer than a cloudy afternoon back home. The sky there is not blue. It is a soft, smoky orange, the color of weak tea held up to a lamp. That orange color is the first great clue to what makes this moon so strange. Titan is wrapped in a thick atmosphere. It is the only moon in the solar system with a real atmosphere worth speaking of, and it is denser than the air you are breathing right now. If you could stand on Titan's surface, the air would press on you about 1.5 times harder than the air at sea level on Earth. The atmosphere is made mostly of nitrogen, just like ours, but mixed with methane and a long list of other carbon compounds. These compounds form a permanent orange haze high above the surface, a soft veil that hides the ground from view. For most of human history, that veil kept Titan a complete secret. Through a telescope, it looks like a small fuzzy dot, blank and featureless. We knew it was there. We did not know what it looked like underneath. Even when spacecraft began visiting Saturn in the 1980s, the cameras saw nothing but smooth orange clouds. The surface, whatever it was, lay hidden. Titan is old. It formed alongside Saturn about 4.5 billion years ago, in the same swirling disk of gas and dust that built the Sun and the planets. So it is roughly the same age as Earth, give or take. But the materials that came together to make it were different. Out at Saturn's distance, the swirling disk was cold enough that water existed as solid ice from the very beginning. The Titan is built largely from that ice, mixed with rocky material in its deep interior. Its surface is not made of stone the way ours is. It is made of water ice, frozen so hard at -290 degrees Fahrenheit that it behaves like rock. That cold is the second great clue. At Titan's temperatures, water cannot flow. It is locked into the crust as a kind of ice bedrock. But methane and ethane, which we know on Earth only as gases that burn in stoves and lighters, behave very differently in that cold. There they become liquid, they pool, they flow. They evaporate, they fall again as rain. That is the puzzle this whole episode rests on. Titan has weather and seasons and lakes and rivers and clouds and storms. It has a full hydrologic cycle, the kind of system Earth has. But the working fluid is not water. The water is the ground. The liquid running through the channels and gathering in the basins is something else entirely. And no one is quite sure how complete that picture really is, how deep the lakes go, how often the rain falls, or what might be stirring beneath the frozen crust. Hold that idea in your mind as we go further. The world the size of a small planet, air thicker than our own, an orange sky, a bedrock of ice, and rivers somewhere down there made of something that on Earth we would never call a river at all. To understand the rain on Titan, we have to go back, far back to the time when the sun itself was still young and the great disk of dust and gas around it had not yet finished settling into worlds. In that distant era, somewhere past the line where water freezes solid in space, a small world began to gather itself together. It pulled in ice and rock and the leftover crumbs of a forming solar system. Slowly, over many millions of years, those pieces stuck and pressed and folded into the moon we now call Titan. The exact details of this birth remain uncertain. One idea is that Titan formed inside a smaller disk of material that swirled around the young Saturn, like a tiny solar system within the larger one. In this view, Titan grew up alongside its sibling moons, each gathering its share of ice and stone. A different idea suggests that Titan may have formed from the merging of several smaller moons, after some early disturbance broke them apart and let them stick together again. Both ideas have their supporters. The evidence is incomplete, and the truth may be stranger than either guess. What we do know is that the deep cold of the outer solar system gave Titan something rare. Out there, far from the warmth of the sun, water freezes as hard as stone. But other substances, ones that would be gases on a warm world, can settle into liquids and ices of their own. Methane and ethane, simple molecules made of carbon and hydrogen, can pool and flow at those frigid temperatures. And so, as Titan cooled and aged, the stage was quietly set for a different kind of weather. The air came next, or perhaps the air came alongside everything else. Researchers are still working out exactly when and how Titan gained its thick blanket of nitrogen. Some think the nitrogen was trapped inside the ice that built the moon, locked away in tiny pockets, and slowly released as the interior warmed. Others suspect it formed later, when ammonia from deep inside broke apart under sunlight and chemistry, leaving nitrogen behind. The truth is still being pieced together, one careful measurement at a time. However it arrived, the air gathered and thickened. It grew dense enough to press down on the surface harder than the air on Earth presses on us. And within that dense air, methane began to play the role that water plays on our own world. It rose as vapor, it cooled, it gathered into clouds, and in time it fell. The rain on Titan does not fall the way ours does. The drops are larger, fatter, softer. They form in a sky so cold that everything moves at a different pace. The air is thick and the gravity is gentle, so a methane raindrop drifts down slowly, almost like a feather in syrup. A single drop might take many minutes to reach the ground from the cloud where it formed. In some places, it may not even arrive. It can evaporate again on the way down, returning to the sky before ever touching the orange-tinted surface. When the rain does land, it does what rain does. It pools, it runs, it carves shallow channels into the icy bedrock. Over long stretches of time, those channels deepen and branch. They wind across the dim landscape, gathering into wider streams, spilling into low basins, and eventually settling into broad, still lakes of liquid methane and ethane. The whole cycle echoes the one we know from home, only shifted into a colder key, with different chemistry singing the same old song. How long did this take to build? We do not know with certainty. Titan is roughly 4.5 billion years old, like the rest of the Saturn system, but the surface we see today is far younger in places. Some regions look freshly resurfaced. Others look old and weathered. The lakes themselves may come and go on timescales we can barely imagine, filling during long wet seasons and slowly drying during long dry ones. A single Titan year lasts almost 30 Earth years, so even one full turn of its seasons stretches across a human lifetime. There is a quiet beauty in this slow becoming. The world born in deep cold, gathered from ice and dust, wrapped in a heavy golden haze, learning over billions of years to make rain out of fuel and lakes out of fog. How exactly each step unfolded is still an open question. Researchers gather hints from spacecraft, from telescopes, from the patient work of comparing one model with another. For now, the origin of Titan's slow rain remains a story still being written, one careful drop at a time. To understand Titan's lakes, we have to think about a chemistry that feels almost backwards. On Earth, water is the great solvent, the patient liquid that carves canyons and fills oceans and runs in our blood. On Titan, water cannot do any of that. The surface is so cold, around minus 180 degrees Celsius, that water there is hard as granite. It forms the bedrock of the mountains and the gravel in the riverbeds. In place of water, a different molecule has taken over the work of weather and rivers and seas. That molecule is methane. On Earth, methane is a gas. It seeps from swamps and drifts from the mouths of cows and rises from the muddy bottoms of lakes. Here it floats invisibly through the air. But on Titan, methane behaves the way water does at home. It pools, it flows, it falls as rain. The same molecule, just placed in a colder world, becomes something almost unrecognizable. It is a quiet reminder that what a substance does depends as much on its temperature as on what it is made of. Methane is a simple thing. One carbon atom, 4 hydrogen atoms, bonded in a tidy little shape like a tiny pyramid. Mixed with it in Titan's lakes is ethane, a slightly larger cousin made of 2 carbon atoms and 6 hydrogens. The exact balance of methane to ethane in any given lake is still a question researchers are working on. Some lakes seem richer in methane, others seem to hold more ethane. The northern seas may be different from the southern ponds. We have measurements from a few places and educated guesses about the rest. Both of these molecules belong to a family called hydrocarbons. They are the same family that makes up natural gas and gasoline and candle wax back home. On Earth we burn them. On Titan there is almost no oxygen in the air, so nothing burns. The hydrocarbons simply sit there, pooled in great cold lakes, drifting through the haze, falling as occasional rain. A world soaked in fuel that can never catch fire. These building blocks did not appear from nothing. Carbon, the backbone of every methane molecule on Titan, was forged inside ancient stars. Deep in stellar cores, hydrogen fused into helium, and helium fused into carbon, and when those stars finally died they scattered their carbon into the dark between worlds. Some of that carbon drifted into the cloud that became our sun. Some of it settled into the bodies of the outer planets, and some of it ended up bonded to hydrogen, making the methane that now falls as rain on a distant moon. The hydrogen is older still. Most of the hydrogen in the universe was made in the first few minutes after the Big Bang, when the cosmos was hot and dense and young. The hydrogen atoms in Titan's lakes have been drifting through space for nearly 14 billion years. They were there before the sun was born. They will be there long after it cools. Each raindrop on Titan carries a little piece of the early universe inside it. How exactly Titan ended up so rich in methane is one of the questions that still bothers researchers. One possibility is that the methane was trapped inside ice during the moon's formation and slowly leaked out over billions of years. And another idea is that some of it is being made fresh, deep underground, by chemical reactions between water and rock. A third possibility is that comets and other icy bodies delivered organic material as Titan grew. The honest answer is that we do not yet know which of these stories is closest to the truth. It may be all of them in different amounts layered together. There is also the puzzle of the haze. High above the lakes, sunlight breaks apart methane molecules and stitches the pieces back together into larger compounds. These larger molecules drift downward, slowly, like soot from an invisible chimney. They coat the surface in a fine dark dust that mixes with the sand and settles in the basins. The chemistry up there is complicated, full of nitrogen compounds and carbon chains, whose exact identities researchers are still sorting out. Some of these molecules have never been observed anywhere else in the solar system. So Titan's chemistry sits at a strange crossroads. Familiar atoms, arranged in familiar ways, behaving in unfamiliar roles. Hydrogen from the first moments of time. Carbon from the hearts of long-dead stars. Together they make a rain that is not water, and a sea that is not water, and a sky full of haze whose recipe we are still trying to read. Far in the north of Titan, near the top of that pale orange globe, there sits a sea. It is called Kraken Mare and it is the largest known body of liquid on the Moon. Its shoreline is long and crooked, with bays and channels and quiet inlets. If you could stand on a cliff above it, you would see a dark, glassy surface stretching to a hazy horizon. The liquid would not be water. It would be a slow, cold mixture of methane and ethane, the kind of stuff we use as fuel on Earth, here cooled to a temperature that would freeze the breath in your lungs. Kraken is large. By the best estimates from the Cassini spacecraft, it covers an area bigger than all 5 of Earth's Great Lakes combined. In some places, it may be more than 300 meters deep, though the true bottom has never been directly measured. The radar on Cassini sent pulses down through the haze and listened for the echo. In parts of Kraken, no echo came back at all. That silence could mean the sea is simply too deep for the signal to return. Or it could mean the liquid there absorbs radar in a way we do not yet fully understand. The question is still open. Several forces shape this strange northern sea. The first is gravity, but a gentler gravity than ours. Titan pulls on objects with only about 1/7 of Earth's strength. A wave that would crash hard on a beach at home would rise slowly here, lift in a long arc and fall back without much sound. The liquid itself is less dense than water, and the air pressing down on it is thicker than our own. All of this together means waves on Kraken should be lazy, low and wide. For years, in fact, the surface of these northern seas looked almost too still. Cassini watched and watched, and the radar returns came back smooth, as if Kraken were a mirror. Some researchers wondered whether a thin film of frozen material lay on top, calming everything beneath. Others suggested the winds were simply too weak in Titan's long winter to stir the liquid at all. Later, as the seasons changed and summer crept north, faint glints appeared. These were called sun glints. They were brief, bright sparkles that may have been small ripples catching light. Whether those ripples were waves driven by wind or rising bubbles of nitrogen escaping the depths is still debated. Tidal forces also work on Kraken, though softly. Titan moves around Saturn in a slightly stretched orbit. As it draws closer to the giant planet and then swings outward again, Saturn's gravity pulls on Titan's seas with a rhythm that lasts about 16 Earth days. Each full circle, the surface of Kraken may rise and fall by a small but real amount. The tide is not crashing or dramatic. It is a slow breathing, a quiet swelling repeated over and over for as long as the Moon has existed. Beneath the surface, pressure builds with depth, just as in our oceans. Cold methane and ethane behave a little differently from water, though. They can dissolve nitrogen from the thick air above, holding it within the liquid like soda holds its fizz. When temperatures or pressures change, that nitrogen can come out of solution and rise as bubbles. Some scientists think these bubble events might explain certain strange bright patches Cassini saw, features that appeared briefly and then faded. The idea has a nickname. They call them magic islands, though no one believes they are truly islands. What they actually are remains one of Titan's quieter mysteries. Heat, of course, is in short supply this far from the Sun. The sunlight reaching Titan is roughly 1% of what reaches Earth. Yet the methane cycle keeps going, fed by the tiny warmth that does arrive, and perhaps by gentle heat leaking up from the moon's interior. We do not know for certain how much internal warmth there is, or how steadily it flows. Saturn's magnetic field also reaches Titan, washing the upper atmosphere with charged particles. Down at the surface of Kraken, that field is faint and far away, but it helps shape the chemistry of the air that eventually rains back into the sea. So Kraken sits there in the dim orange light, pulled by Saturn, breathed on by faint winds, fed by methane rain and quietly hiding its depths. We have looked at it from far above, but no craft has ever floated on it. Until something does, the sea will keep its secrets folded beneath its still and patient surface. Picture a riverbed cut into pale ice. It winds across the land in gentle curves, branching like the veins on the back of a leaf, with smaller streams feeding into larger ones and larger ones flowing toward a distant shore. From above, it looks like any river system you might see from an airplane window on Earth. The shape is familiar. The pattern is familiar. Only the substance is wrong. These channels on Titan were carved by liquid methane. And to understand what that means, it helps to sit for a moment with the strangeness of the cold. On Earth, the coldest natural place ever measured sits in Antarctica, where the air can drop to about -89 degrees Celsius. That kind of cold can crack steel and freeze breath into glittering crystals before it leaves your mouth. Titan's surface is colder than that, much colder. The average temperature there hovers near -179 degrees Celsius. If you took the coldest day ever recorded on our planet, and then subtracted another 90 degrees, you would be standing on a warm afternoon by Titan's standards. At that temperature, water is no longer a liquid. Water ice on Titan is as hard as granite. It forms the bedrock of the moon. The boulders that line the riverbanks, the cliffs that rise above the plains, the hills that catch the dim sunlight, all of it is frozen water, locked into place so firmly that it behaves like stone. So the rivers cannot be carrying water. The water is the ground itself. The thing doing the carving has to be something else, something still liquid in that profound chill. And the answer, as far as we can tell, is methane. Methane, which on Earth is a gas that hisses from kitchen burners. Methane, which only becomes liquid if you cool it past -161 degrees Celsius. On Titan, it pools in valleys and falls from clouds. Now think about the scale of these channels. Some of them are short, only a few kilometers long, the way a small mountain stream might tumble down a hillside near a quiet town. Others stretch for hundreds of kilometers. One large channel network on Titan, mapped by the Cassini spacecraft, runs over 400 kilometers before reaching the shoreline of a northern sea. That is roughly the distance from New York City to the outskirts of Boston. A river of cold hydrocarbons running quietly across an alien world, longer than many of the famous rivers of Europe. The shapes of these channels look astonishingly like the rivers of Earth. Some have meanders, those slow looping bends that form when a current pushes against soft banks. Some have braids, where a single channel splits into many smaller threads across a flat plain. Some sit at the bottom of steep canyons. One canyon system on Titan, called Vid Flumina, was measured by radar to be around 0.5 kilometer deep in places. Imagine standing at the rim of a gorge nearly twice as deep as the Empire State Building is tall, with dark methane flowing far below at temperatures that would shatter any living thing from Earth instantly. The walls of that canyon are water ice. The river inside is liquid natural gas. The rain that fed it fell in slow, fat drops through an orange sky. How long did it take to carve these channels? That part remains an open question. On Earth, a river the size of the Colorado spent millions of years cutting the Grand Canyon. On Titan, the rainfall is gentler and far less frequent. Heavy storms may strike a given region only once in many Earth years, perhaps once in a generation, perhaps even less often than that. Some researchers wonder whether the channels were cut quickly, during rare and violent floods that swept across the surface. Others suspect they formed slowly over millions of years by the patient work of light, steady drizzle. Both ideas have evidence to support them. Neither has been settled. There is also a quieter possibility. Some of the channels we see may be ancient, carved during an earlier era when Titan's climate was different, when methane was more abundant in the atmosphere, when the rains were heavier. They may be the riverbeds of a vanished season, still holding their shape in the frozen ground long after the water, or rather, the methane has gone. When you picture them tonight, picture them empty in places, picture them full in others. Picture the slow shine of a liquid that is not water, moving through valleys cut into ice that is not stone, beneath a sky that is not blue. The familiar shape of a river, the unfamiliar substance inside it, and the unanswered question of how long it took to carve. Imagine for a moment that you could float, slow and quiet, above the surface of Titan. The first thing you would notice is the color. Everything is washed in a soft amber light, like the last hour of a long autumn afternoon. The sky above you is not blue. It is a deep, hazy orange, thick with tiny particles that scatter the faint sunlight into a warm, honey-colored glow. Even shadows here are gentle. The light is so diffused by the haze that the world below seems to give off its own quiet warmth, though the air around you is colder than anything you have ever felt. Beneath you, the ground is dark. Not black exactly, but a deep, dusky brown, the color of damp coffee grounds or wet bark. In places it looks almost purple where the orange light meets the shadowed valleys. The crust you are drifting over is not soil or rock in the way Earth has soil or rock. It is water ice, frozen so hard at -179 degrees Celsius that it behaves like stone. Tap it, and it would ring like granite. Over this icy bedrock, a thin coating of dark organic dust has settled, the slow rain of chemistry that drifts down from the orange sky above. You see hills in the distance, rounded and worn, their slopes streaked with paler ribbons where something has flowed. The hills are not tall. Titan's terrain is mostly gentle, with broad plains and low ridges, softened by ages of rain and wind. Some of the hills shine a little brighter than the surrounding ground. Researchers think these bright regions may be exposed water ice, scrubbed clean by methane runoff. Others wonder if the brightness comes from a different kind of frost, perhaps a coating of clean organic crystals. The answer is not yet settled. Above the hills, clouds drift. They do not look like the clouds you know. They are wispy, layered, sometimes appearing as long, pale streaks, sometimes as soft puffs near the poles. These clouds are not made of water. They are made of methane and sometimes ethane, and they form at altitudes far higher than most clouds on Earth. From your floating vantage point, you can see them moving slowly, very slowly, pushed by winds that are gentle near the ground but stronger in the upper atmosphere. The whole sky seems to breathe in slow motion. If you watch one of these clouds long enough, you might see a faint shimmer beneath it. A column of falling droplets. Methane rain. The drops are larger than Earth's raindrops, perhaps twice the size, and they fall slowly, almost lazily, through the thick air. A single drop might take minutes to reach the ground. From this height, the rain looks like a soft brushstroke against the orange light, a hanging veil of liquid that drifts sideways as it falls. Lower down, you can see where past rains have gone. There are dark patches that look like spilled ink on the ground, smaller pools that may be shallow lakes of methane and ethane mixed together. Near the equator, many of these depressions look dry, their floors paler than the surroundings, as if a lake had once filled them and then slowly evaporated. Whether the equator was once wetter, or whether these dry basins formed in some other way, is one of the open questions Titan keeps to itself. The horizon curves softly in the distance, blurred by the haze. You cannot see far, maybe a few dozen kilometers before everything dissolves into amber mist. There is no sharp line where ground meets sky. Instead, the two blend together in a slow gradient of brown into orange into gold. It gives the world a closed-in feeling, intimate almost, as if you are floating inside a vast lantern. The silence here would be unusual. Titan's atmosphere is denser than Earth's, so sound would travel well, but there would be little to hear. Perhaps the soft hiss of wind across a dune, perhaps the patter of slow, heavy drops. Perhaps nothing at all. The whole landscape feels patient, as if it has been waiting a very long time for someone to notice it. What we are describing comes partly from what the Huygens probe saw during its brief descent in 2005. Partly from radar maps made by the Cassini spacecraft, and partly from careful guesswork. Much of the surface remains hidden under the haze, and much of what we think we see is still being debated. Whether the bright streaks are ice or frost, whether the dark patches are wet or dry, whether the clouds we glimpse are common or rare, all of these remain quiet, lingering questions in the orange twilight. To stand on Titan would be to stand inside a clock that ticks more slowly than any clock on Earth. The seasons there do not pass in months. They pass in years, and then in handfuls of years, and then in something closer to a human lifetime. One full trip around the Sun takes Saturn nearly 30 Earth years. Titan rides along with Saturn, so its seasons stretch out to roughly 7 Earth years each. That long, slow rhythm shapes everything beneath the orange haze. A spring on Titan is not a few warm weeks. It is a slow brightening that lasts almost a decade. A summer is a long, gentle tilt of one pole toward the distant sun. Winter is a quiet shadow that creeps across the same pole for years at a time. The world breathes in and out, but each breath takes a generation. Beneath the haze, this slow rhythm seems to move the weather in strange ways. When Cassini watched Titan over its long mission, scientists noticed that clouds drifted from one hemisphere to the other as the seasons changed. Methane storms gathered near the summer pole, then faded, then formed again in new places. Lakes in the north grew while lakes in the south seemed to shrink. The whole moon appears to slosh its liquid methane slowly from one half to the other, like a bowl tipped a tiny bit at a time. But how deep does this seasonal shift really go? That is one of the open questions. The lakes we can see on the surface may be only the top layer of something larger. Some researchers wonder if methane and ethane soak down into the icy crust, the way water soaks into soil on Earth. If so, there could be a kind of hidden reservoir beneath the visible lakes. A slow, cold groundwater system, except the groundwater is not water at all. One idea suggests that Titan has a buried layer of porous ice, full of tiny gaps and channels. Liquid hydrocarbons could trickle down into those gaps and pool there, far from the wind and the weak sunlight. If that picture is right, the surface lakes might rise and fall partly because this hidden layer is filling and draining with the seasons. Other researchers are not convinced. They think most of the seasonal change happens in the atmosphere itself, with the surface lakes responding only slightly. The truth probably sits somewhere between, and we do not yet have the measurements to say. Deeper still, the picture grows even stranger. Beneath the icy crust, many scientists believe Titan hides a vast ocean of liquid water mixed with ammonia. This buried ocean would sit perhaps 50 to 100 kilometers below the surface. It would be dark, salty, and pressed under enormous weight. The slow seasons on the surface would barely touch it. Down there, time would move in a different way, measured not in years but in the slow churn of warm rock far below. Between the buried ocean and the surface lakes lies a thick shell of water ice. That shell is so cold it behaves like stone. The mountains on Titan are not made of granite. They are made of frozen water harder than concrete, sculpted by methane rain into shapes that almost look like familiar hills. When the long summer warms the surface by a degree or two, the icy shell barely notices. It holds the buried ocean in like a sealed jar. The question of how these layers talk to each other is still wide open. Does any of the buried water ever reach the surface? Some researchers think yes, through cryovolcanoes, volcanoes that erupt slushy ice instead of molten rock. Others think the crust is too thick and rigid for that. If water does sometimes seep upward, even rarely, it would mix with the surface organics in ways that could matter for chemistry, and perhaps for something stranger than chemistry. If it never reaches the surface, then Titan is really two worlds stacked together, each with its own rhythm, separated by a wall of ice. For now, all we can do is watch the long seasons turn. A child born when Cassini first arrived at Saturn would be old enough to drive a car by the time a single Titan season ended. The clouds we saw in the north years ago have already begun to fade. New ones are gathering in places where the sun is just starting to warm the haze again. Beneath them the lakes wait. Beneath the lakes perhaps a hidden layer breathes, And beneath all of that, an ocean we have never seen waits in the dark, keeping its own slow time. Across the wide middle belt of Titan near the equator, the land changes its character. The bright icy plains give way to long stretches of darkness, ribbed and combed like the back of some sleeping animal. These are the dune fields of Titan, and they stretch for thousands of miles. From orbit, they look like the dark seams of a great patterned cloth, running mostly east to west, wrapping the moon in soft, parallel lines. The dunes are tall. Many rise about 100 meters from base to crest, taller than a 30-story building. They march in long ridges, sometimes for hundreds of kilometers without a break, bending only when they meet a hill or a bright icy island in their path. If you could stand among them, you would see slopes of dark grains stretching to the horizon, slowly shaped by winds you can barely feel on your skin. The grains themselves are the first puzzle. They are not made of rock or quartz, like the sand on a beach back home. The dunes of Titan appear to be built from dark organic particles, the carbon-rich dust that drifts down from the orange haze above. Methane and nitrogen high in the sky react under sunlight and form complex molecules. Those molecules clump together, grow heavier, and eventually fall. Over long ages, this slow snow of carbon may have settled across the equator and piled into mountains of soft, dark sand. There is a rhythm to this. Titan has seasons, each one about 7 Earth years long, and with the seasons come shifts in wind and weather. Researchers think the dunes record those rhythms in their shape. The way the ridges align, the angle of their crests, the small ripples on their flanks, all of these are written by wind over time. The dunes are a kind of slow clock, ticking once every Saturn year, which is nearly 30 of ours. The wind itself is part of the mystery. Models of Titan's atmosphere once suggested the surface winds near the equator should blow from east to west. But the dunes appear to point the other way, shaped as if the wind that built them came from the west. One idea is that the dominant winds only blow during rare, stronger gusts that arrive with the changing seasons, and those gusts override the gentler everyday breeze. Another possibility is that storms near the equinox, when sunlight shifts from one hemisphere to the other, set the pattern. Researchers are still working through these ideas, and the question of what really sculpts the dunes remains open. The cycle of the grains themselves is also unsettled. We do not know exactly how the dust from the sky becomes sand on the ground. The particles that drift down from the haze are extremely fine, more like soot than like beach grains. Something must gather them into pieces large enough to roll and tumble across the surface. One theory suggests that the rare rains of liquid methane wet the dust, cause it to clump, and then leave behind small dry pellets when the methane evaporates. Another theory points to static electricity, which seems to behave strangely in Titan's dry, cold air. Tiny grains may cling to one another by electric charge, building up over centuries into sand-sized lumps that the wind can carry. There are quiet places between the ridges, narrow corridors of brighter ground where the dunes have not reached. From above, these gaps look like pale rivers winding between dark forests. Whether anything flows through them, even rarely, is not known. They may be old channels carved by methane floods long ago, or they may simply be low spots the sand has not yet filled. The dune fields seem to grow and shift, but on a timescale far slower than any human life. The dunes also avoid the highest latitudes. They cluster near the equator and fade as you move north or south, giving way to plains, then to lakes and seas near the poles. This pattern hints at a global cycle, where moisture and dust move from one part of Titan to another over the long seasons. Methane may rain in the north for one Saturnian summer, then shift south for the next. Dust may build up in the dry middle band while the poles fill with liquid. The whole moon breathes slowly, in and out over decades. It is a strange thing to imagine a desert made of soot, ridged by winds that blow once a generation, surrounding a world that rains. The dunes hold their secrets in their dark slopes, and what they truly record about Titan's ancient weather is a question still waiting for an answer. Beneath the lakes of liquid methane, beneath the dark dunes and the slow rivers, Titan has a floor. And that floor is not stone the way we know stone on Earth. It is ice. Water ice frozen so cold that it behaves like rock. This is one of the strangest neighbours any landscape could have. On our world, water is the soft thing. It pools, it flows, it shapes the land slowly over thousands of years. On Titan, water plays the opposite role. It is the hard, unmoving bedrock, the thing the methane rivers cut into, the thing the dunes rest upon. At Titan's surface temperature, around -290 degrees Fahrenheit, water ice is as solid and stubborn as granite. Picture standing on a ridge of pale ice that has not melted in billions of years. Above you, an orange sky. Below your boots, a frozen crust harder than any glacier on Earth. Around you, sand that is not sand at all, but dark grains of organic material drifting against icy slopes. It is a world built from familiar parts arranged in unfamiliar ways. The ice itself may not be pure. Researchers think it is mixed with other frozen compounds. Ammonia could be locked inside it. So could various hydrocarbons that have settled out of the sky over long ages. The exact recipe of Titan's crust is still an open question. Different studies of the moon's gravity and radar signals have given different hints, and no single picture has won out yet. What we can say is that the ice is thick. Estimates suggest the crust may stretch down many tens of miles before it gives way to something else, and that something else is, we believe, more water. A hidden ocean of liquid water, salty and dark, sealed between the icy shell above and a deeper layer of high-pressure ice below. We will sit with that hidden ocean in a later section. For now, simply hold the image of it in mind. A frozen sky of solid water with a liquid water sea beneath and methane rain falling on top of it all. The neighbours of Titan's lakes are not only beneath them, they are beside them too. The shoreline of a methane sea is bordered by hills of water ice. The riverbeds are carved through valleys of ice. Wind blows organic dust across ice plains. Everything here touches everything else, and yet the chemistry stays separate in surprising ways. Liquid methane does not dissolve water ice the way liquid water would dissolve rock salt back home. The ice is mostly inert at these temperatures. It sits quietly while the methane moves around it. This raises one of the gentler mysteries of Titan. If the ice does not dissolve, how exactly do the rivers carve their channels into it? One possibility is mechanical erosion, the slow grinding of sediment carried by the flow. Another idea is that small amounts of other compounds in the methane act as a weak solvent over long stretches of time. A third possibility is that the channels formed during older, warmer episodes in Titan's past, when the chemistry behaved differently. The question stays open. The river valleys are real. The mechanism that shaped them is still being worked out. There is also the matter of how the crust connects to the deeper world. Some models suggest the icy shell is rigid and locked in place. Others suggest it can shift, very slowly, floating on the hidden ocean beneath like a vast frozen raft. Measurements of how Titan's surface features drift over the years have offered hints, but the readings have changed as new data has come in. Whether the crust slides and how freely remains uncertain. And then there are the slow exchanges. Material from the atmosphere settles onto the ice. Methane seeps into the crust and may travel down through cracks. Heat from below may rise in pockets and warm small regions of the surface. Titan's neighbours, in other words, are not just sitting next to one another. They are quietly trading with one another across enormous spans of time. Stand on that frozen ridge again. Look down at the dark methane sea lapping against pale ice. Look up at the soft orange haze. Imagine the salty water ocean miles below your feet, completely hidden, completely silent. 3 different liquids, 3 different solids, all layered together in one small world, each one bordering the next, each one shaping the others in ways we are still trying to understand. The bedrock of water ice is the quiet stage on which all of Titan's strangeness plays out. Familiar in name, foreign in behavior. A frozen reminder that the same materials, placed in different conditions, can build worlds we barely recognize. Far below the cold orange skin of Titan, deeper than the methane lakes and the dunes of dark sand, something even stranger may be waiting. Beneath the crust of water ice that wraps the whole moon like a frozen shell, scientists believe there is a hidden ocean. Not an ocean of methane, not an ocean like the seas on the surface. An ocean of liquid water, vast and dark and quiet, sealed away from the sky. This buried sea may be one of the largest bodies of liquid water in the entire solar system. Some estimates suggest it could hold more water than every ocean on Earth combined. It would stretch all the way around the moon, a single global layer trapped between ice above and ice below. And nobody has ever seen it. Nobody knows exactly how deep it goes. Nobody knows what, if anything, drifts within it. The evidence for this ocean is gentle and indirect. When the Cassini spacecraft watched Titan over many years, it noticed that the moon's surface seemed to shift slightly as it orbited Saturn. The crust appeared to flex, almost like a soft shell sliding over something liquid underneath. That subtle motion is one of the strongest hints we have. It suggests the ice is floating on a layer that can move, a layer that can yield, a layer that behaves like a sea. The temperatures involved are among the most extreme you can imagine. The surface of Titan sits at around -179 degrees Celsius, cold enough to freeze gasoline solid in moments. Yet just 100 kilometers or so below your feet, if you could stand there, the temperature climbs back up toward the freezing point of water. The pressure rises, the ice softens, and somewhere in that transition, liquid water begins. What makes this ocean even stranger is what it might contain. Researchers suspect the water is not pure. It may be heavy with dissolved salts, perhaps ammonia, perhaps other compounds leached from the rocky core far below. Ammonia would act like an antifreeze, lowering the temperature at which the water freezes and keeping the ocean liquid even in such bitter cold. One theory imagines a briny, slightly soapy sea, dense and slow-moving, sloshing in perfect darkness. Another theory goes further. Some researchers wonder whether warmth from the rocky core could still be leaking upward, gently heating the base of the ocean. If that is true, the seafloor of this hidden world might not be a dead place at all. It might have slow currents, it might have chemistry, it might have the kind of slow exchange between rock and water that, on Earth, gives rise to deep-sea vents teeming with life. Whether any of that exists on Titan remains completely unknown. The depth itself is hard to picture. The ocean may begin perhaps 50 to 100 kilometers below the surface and extend downward for hundreds of kilometers more. Beneath that lies another layer, a strange high-pressure ice that forms only when squeezed by enormous weight. This deep ice is different from the ice on the surface. It is denser, more tightly packed, and it sinks rather than floats. The ocean would be sandwiched between two kinds of ice, a thin liquid layer pressed between frozen worlds. That sandwich raises one of the great open questions about Titan. On other icy moons like Europa, the ocean sits directly on rock. That contact between water and stone is what makes Europa so interesting to astrobiologists. On Titan, the rocky seafloor may be buried beneath that high-pressure ice, sealed away from the water above. If nothing can pass through, the ocean may be chemically isolated, cut off from the minerals that life as we know it tends to need. Or there may be cracks, there may be slow seepage. The truth lies hidden under layers we cannot drill through. There is also the question of connection. Does anything from the surface ever reach the buried sea? Methane and other molecules fall as rain, settle into the lakes, sink into the crust. Over millions of years, could some of that material work its way down through fractures in the ice and mingle with the ocean below? Some models suggest yes, at least slowly. Others suggest the icy lid is too thick, too sealed, too patient. The exchange, if it happens at all, would unfold across timescales that dwarf human history. For now, the hidden ocean of Titan remains one of the great unseen places in the solar system. Larger than Earth's seas, older than any civilization, locked beneath an orange sky and a crust of ice, we know it is probably there, we do not know what it holds. And that quiet uncertainty is part. Of all the quiet wonders Titan offers, one of the gentlest is the air itself. The atmosphere there is thick, much thicker than ours. At the surface, the pressure is about 1.5 times what you feel right now at sea level on Earth. That alone might not sound remarkable. But when you combine that dense air with Titan's low gravity, something almost dreamlike becomes possible. A person standing on Titan would weigh only about 1/7 of what they weigh on Earth. The air around them would be 4 times denser than ours. And with those two numbers working together, scientists have done the simple math and arrived at a soft, astonishing answer. A human being wearing wings strapped to their arms could likely fly, not glide, not fall slowly. Actually flap, lift off and move through the orange sky under their own power. The motion would be slow, almost graceful, like swimming through cool, heavy water. This is one of those small details that scientists return to again and again, because it sits at the edge of pure poetry. No other place we know of in the solar system offers this gift. The Moon has no air at all. Mars has air so thin it could barely hold up a paper kite. Venus has air thick enough to crush a submarine. Only Titan, far out in the cold, offers the right balance. A sky you could move through with your own 2 arms. The air is mostly nitrogen, about 95% of it, which is similar to the air you are breathing now. The rest is mainly methane, with a thin sprinkling of hydrogen and other trace gases. You could not breathe it. There is no free oxygen, and the cold would freeze your lungs in moments. But the chemistry of that nitrogen-methane mix is part of what makes Titan so strange and so beautiful. Sunlight breaks the methane apart high in the atmosphere. The fragments drift down, joining and rejoining, building heavier and heavier molecules as they fall. Some of these molecules are the same kinds of organic compounds that, on Earth, became the building blocks of living things. Whether they ever do anything similar on Titan remains an open question. Some researchers wonder if the slow rain of these compounds, gathering on the surface over billions of years, has built up layers many meters thick. Others suspect much of it dissolves into the methane lakes or gets buried beneath the dunes. The full picture is still being worked out. There are quieter details too. The sky on Titan is not blue. It is a soft, hazy orange, dimmed by layers of suspended particles that filter the sunlight. Even at midday, the surface receives only about 1% of the light Earth gets. It would feel like a deep, smoky dusk that lasts for hours. The shadows would be long and gentle. The horizon would fade into haze rather than meeting a sharp line. You would not see stars through that haze. You might not even see Saturn hanging just beyond the clouds. And the sounds, or rather what little we know of them. The Huygens probe, the small craft that descended through Titan's atmosphere in 2005, carried a microphone. It recorded the faint hiss of wind during its parachute descent. A real recording from another world of air moving past a falling instrument. The sound is soft and grainy. It is the only audio we have from the surface of a body in the outer solar system. Scientists who listen to it often describe a quiet thrill. Something simple and human, captured in a place no human has ever stood. Sound itself would behave differently in that dense, cold air. A voice would carry a little farther. The pitch of things would shift slightly lower. A bell, if you rang one, would sound deeper than it does here. Footsteps on the icy crust would echo gently. Wind would have a different texture. Whether these subtle changes would feel strange or familiar to a visitor, we cannot really say. No one has been there to listen. The atmosphere also extends remarkably high. Titan's haze layer stretches hundreds of kilometers above the surface, far higher in proportion than Earth's. From orbit, the Moon looks larger than it really is, swaddled in that gauzy envelope. The transition from sky to space is gradual, soft. There is no sharp edge to where the air ends. These are the quiet details, the flying. The orange dusk, the recorded whisper of an alien wind. None of them solve the larger mystery of what Titan is or what it might be becoming. They simply sit there, waiting, patient as the Moon itself. When the Cassini spacecraft first turned its radar eyes toward Titan, the team back on Earth expected to see something familiar. Every other moon in the outer solar system wears its history on its face. Craters cover them. Some are old and softened, some are sharp and young. By counting craters, planetary scientists can read the age of a world like the rings inside a tree. More craters mean more time. Fewer craters mean something has been at work, erasing the record. Titan broke this rule almost at once. As the radar images came down slice by slice through the orange haze, the surface looked oddly smooth. There were dunes. There were river channels. There were broad, dark plains and bright, rugged highlands. But the craters, the deep, round scars that should have been everywhere, were missing. Only a small number have ever been found. On a world that has surely been struck many times over billions of years, this absence is a puzzle that has not yet been fully solved. To understand the surprise, it helps to remember how the discovery unfolded. Cassini reached the Saturn system in 2004 after a journey of nearly 7 years. It carried a small lander built by the European Space Agency, called Huygens, named for the Dutch astronomer who first spotted Titan in 1655. For more than 3 centuries after that first sighting, Titan was little more than a point of light. Its thick orange atmosphere kept its surface hidden from every telescope that tried to peer through. Even the Voyager probes, which flew past in 1980 and 1981, could only photograph the haze. Cassini changed everything. Its radar could see through the clouds. Its infrared cameras could catch certain colors of light that slipped past the haze. Slowly, flyby after flyby, a map of Titan began to form. And as that map filled in, the missing craters became one of the great early mysteries of the mission. There are several ideas about where the craters went. One possibility is that Titan's surface is simply young. If the crust is being resurfaced often, old craters would be buried or erased before new ones could accumulate. Some researchers wonder if cryovolcanoes, slow eruptions of icy slush rather than molten rock, might be smoothing over the land. Others suggest that the methane rain itself is the eraser. Over long ages, that rain could wear down crater rims, fill crater floors with sediment, and round off every sharp edge until the scars vanish. A second idea points to the dunes. Vast fields of dark organic sand cover much of Titan's equator. The grains are not silicate, like sand on Earth, but tiny particles of complex carbon chemistry that drift down from the sky. Wind pushes these grains into long, parallel ridges that stretch for hundreds of miles. If the dunes migrate, they could bury craters under a slow tide of sand, hiding them from radar. A third possibility is more subtle. Titan's thick atmosphere may shield it from smaller impacts. A rock that would punch a crater into an airless moon might burn up or break apart in Titan's dense air before it ever reaches the ground. This would leave only the largest impacts to leave a mark, which fits with what Cassini found. The few craters that exist tend to be big. None of these ideas alone fully explains the pattern. The craters that have been mapped are not evenly spread. Some regions seem older than others. Some craters look fresh with sharp rims. Others look half-melted, as if something has been slowly softening them from below. Whether the answer is rain, sand, ice volcanoes, or some mix of all three, the question is still open. The story of how we learned this is itself a quiet kind of wonder. For more than 300 years, Titan was only a faint dot. Then, in a span of 2 decades, it became a world with rivers and dunes and seas. Each radar pass added a new strip of detail. Each Huygens image, sent during a short descent through the haze in January 2005, gave us a ground-level glimpse of a place no human had ever seen. And in all of that flood of new information, one of the first puzzles to emerge was something missing. Not a strange feature added to the map, but an expected feature absent from it. Tonight, somewhere on Titan, methane rain is falling onto a plain that should be pocked with craters and is not. The wind is moving the dark sand. The ice beneath may be shifting in ways we have only begun to guess. The map is filling in slowly, and the gaps are still doing some of the loudest talking. On Earth, a volcano is a mountain of fire. Hot rock rises from deep below, breaks through the crust and pours out as glowing lava. The ground itself melts and flows. But on Titan, where the surface temperature sits near -179 degrees Celsius, the very idea of a volcano has to change. The bedrock there is not stone. It is water ice, frozen so hard it behaves like rock. And so a different question arises, one that researchers have been turning over for decades. Could Titan have volcanoes made of cold instead of heat? The word for this strange possibility is cryovolcano, a volcano that erupts not molten rock, but a slushy mix of water and ammonia, and other chemicals from somewhere beneath the crust. Imagine an eruption that does not glow red. Imagine instead a slow ooze of cold, salty slush spreading across an icy plain, freezing as it goes, building low domes and gentle ridges. That is the picture some scientists have in mind when they study certain features on Titan's surface. The Cassini spacecraft, which orbited Saturn for 13 years, mapped Titan again and again with radar that could see through its thick orange haze. In some of those maps, researchers spotted shapes that looked oddly familiar. There were rounded mounds with what appeared to be central pits. There were flows that seemed to spread outward from a single point. One region in particular, called Sotra Patera, became a favorite candidate. It has tall peaks, deep hollows and lobes of material that look, at least on radar, very much like the frozen footprints of a slow eruption. But here is where the mystery deepens. Other scientists looked at the same data and were not convinced. They argued that wind, rain, and the slow shuffle of organic sand could shape similar features without any eruption at all. A round pit might be an old impact crater softened by erosion. A lobe of material might be a landslide, or a deposit left behind by a methane river that has since dried up. The evidence is suggestive, but it is not yet a clear yes. This is the part that even seasoned planetary scientists find strange. We have orbited Titan. We have landed on it. We have mapped large portions of its surface, and still we cannot say for certain whether it has active volcanoes of any kind. The thick haze hides too much. The radar sees shapes but not colors, not temperatures, not the small clues that would settle the question. If cryovolcanoes do exist on Titan, they would help explain something else that has long puzzled researchers. Titan's atmosphere is rich in methane, but sunlight should be slowly destroying that methane, breaking it apart into other molecules over millions of years. Something must be refilling the supply. One possibility is that cryovolcanoes are venting methane from a hidden reservoir deep below the crust, slowly topping up the air like a leaky kettle on a low flame. Another possibility is that the methane comes from somewhere else entirely, perhaps released during great cycles of melting and freezing in the deep ice. The question of where Titan's methane comes from remains open, and the cryovolcano idea is only one of several answers being weighed. There is something quietly wonderful about the picture, even unresolved. Picture a low hill on Titan in the long orange twilight. The ground is hard water ice, dusted with dark organic grains. The sky overhead glows a soft amber, and a faint methane mist drifts past. From a crack in the hillside, a slow tongue of cold slush begins to seep. It is not hot, it does not glow. It is colder than anything on Earth could ever be, and yet in Titan's even colder air it is the warm thing. It spreads, slumps, and freezes into a smooth, pale crust. A new patch of ground has been born without a single flame. Whether scenes like that ever truly happen on Titan, no one yet knows. The strongest candidate sites might be cryovolcanoes, or they might be something else dressed up in misleading shapes. The Dragonfly mission, planned for the next decade, may help. It will not visit Sotra directly, but it will study Titan's surface chemistry up close, and the answers it brings back may help us tell eruption from erosion in other places. For tonight, it is enough to hold the picture in mind. A moon where the bedrock is ice, the rain is fuel, and the volcanoes, if they exist at all, breathe out a cold slush instead of fire. A world where even the meaning of the word volcano has to be gently rewritten, and where the final answer is still waiting beneath the haze. In the year 2013, a radar instrument aboard a spacecraft named Cassini was looking down at the northern seas of Titan. It was studying a large body of liquid methane called Ligeia Mare, the second biggest sea on the moon. The radar had passed over this same patch of dark liquid before, and the surface had been smooth and empty. But this time something was there. A bright shape sat in the middle of the sea, where nothing had been seen before. Researchers called it the Magic Island, not because anyone believed it was magic, but because it appeared without warning and would not stay still. In later passes, it changed shape. In some images, it shrank. In others, it grew larger. And then in still later passes, parts of it were gone again. Whatever the bright patch was, it was not behaving like solid ground. This small puzzle is a window into something larger. The Titan is not a frozen, finished world. It is a system in motion. The sea, the sky, the sunlight, and the slow tug of Saturn's gravity all play together in a quiet, ongoing piece of music. The magic island is one note in that song, and we are still trying to hear the whole melody. One idea is that the bright patch was a field of waves. The Titan's seas are so cold, and the air above them so thick, that the liquid sits very still most of the time. But as the seasons change, the winds change too. A gentle breeze sweeping across a glassy sea could lift small ripples. Those ripples might bounce radar back toward the spacecraft, making the surface look bright in just that one spot. If the wind dies, the brightness fades. Another possibility is that bubbles rose from below. Liquid methane can hold dissolved nitrogen, much like a cold soda holds dissolved gas. If the temperature shifts even a little, the nitrogen can come out of the liquid in a soft fizz. A patch of bubbles near the surface would scatter radar in a strange way and make the sea look like something solid was floating there. When the fizzing stops, the island vanishes. A third idea is that something really was floating. The Titan's surface is rich in dark, sooty grains called Tholins, which form high in the atmosphere and drift down like a slow snow of soft soot. Clumps of this organic material might bob along the surface for a while, then break up, then sink. A raft of waxy debris could explain a shape that grows, shrinks, and disappears across many months. We do not know which idea is right. It may even be that different sightings of magic islands have different causes. The point is not the answer. The point is the connection. The sea is not closed off from the rest of Titan. It feels the air above it, the warmth of the distant sun, the chemistry of the sky, and maybe even the heat of whatever lies beneath the crust. Think about how each of these things touches the others. The sun, faint and small at that distance, still pushes the seasons forward in a slow rhythm of about 30 Earth years. As the seasons turn, the winds shift and the winds brush the seas. The same sunlight, weak as it is, drives the chemistry high above, where methane breaks apart and reforms into the dark grains that paint the sky orange. Those grains drift down, settle on the dunes, wash into the rivers, and finally pool in the seas. The sky is feeding the sea. The sea, in turn, may feed the sky. When the air warms by even a fraction of a degree, liquid methane evaporates and rises as a thin haze. Clouds gather. Rain falls somewhere else on the moon, carving new channels into the ice. The system loops back on itself, slow and patient over centuries. And under everything, deep below the icy crust, researchers suspect a hidden ocean of water and ammonia. If that buried ocean shifts even a little, it could warm the crust above it. Gases trapped in the ice could leak upward. Bubbles could rise into a sea like Ligeia. An island could appear. So when the radar caught that bright patch and lost it again, it may have been listening to a chord played across the whole moon. Sky, sea, sun, ice, and hidden ocean, all touching one another in ways we have only begun to trace. The magic island is small. The question behind it is not, how tightly is Titan woven together, and how much of its quiet weather do we still misunderstand? For now, the sea keeps its own counsel, and the bright shapes come and go. High above Titan, in the cold upper reaches of its thick air, something strange is happening right now. Sunlight, weak and far away, is touching molecules of nitrogen and methane. The light breaks them apart. The pieces drift, meet, and join again in new shapes. Slowly, patiently, over time scales we can barely picture, these new shapes build into larger and larger chains. Scientists have a name for the haze they form. They call them Tholins. The word comes from an old Greek root meaning muddy or murky. And that is just what they are. A soft, sooty mist of complex carbon molecules, hanging in layer after layer, painting the sky in shades of orange, gold, and brown. The haze is so dense that for most of the 20th century, we could not see the surface at all. Titan kept its face hidden behind this slow rain of its own making. The Tholins do not stay in the sky forever. Gravity pulls them down. They drift toward the lower air, gathering into larger particles, then settling onto the ground like a fine, dark snow. The fall is gentle. In Titan's thick atmosphere and weak gravity, a single grain may take months or even years to reach the surface. And while it falls, more particles are forming above it. The haze never empties. It refills itself, again and again, with each weak ray of sunlight that touches the top of the air. Over very long stretches of time, this slow rain of organic dust has built up the dark plains and dune fields we see today. The black sands that stretch across Titan's equator are thought to be Tholin material, packed and shaped by the wind. Each dune is, in some sense, a record of millions of years of sky chemistry. The sky is painting the ground, one quiet grain at a time. How quickly this happens, and how the layers change with the seasons, is still an open question. Some researchers think the haze grows thicker in one hemisphere during winter and thins in the other during summer. Observations from spacecraft hint at this kind of seasonal shift. The northern haze cap seems to swell and fade as the sun moves slowly across Titan's long year. But the details remain unclear. Titan's year lasts about 29 Earth years, so a single full cycle of seasons takes most of a human lifetime to watch. Other researchers wonder whether the haze itself is changing over much longer time scales. If the methane in Titan's air is slowly being lost to chemistry, broken apart by sunlight and never fully replaced, then one day the Tholins may stop forming. The sky might clear. The orange veil might thin, then vanish. Some estimates suggest the methane could be used up in tens of millions of years, unless something deep within Titan keeps refilling it. Whether that refilling is happening, and how, remains one of the central puzzles of this world. There are several ideas about where fresh methane might come from. One possibility is that cryovolcanoes, the ice volcanoes we touched on earlier, release methane from inside the moon. Another idea is that a slow chemical churn in the deep interior keeps producing it. A third possibility is that the methane we see now is the last of an ancient supply, and Titan is in a quiet, fading chapter of its own history. We cannot yet tell which of these stories is the right one. What we can say is that the sky is alive with slow change. Every moment, somewhere in the upper haze, a molecule is being broken and remade. Every moment, a grain of Tholin is drifting downward through the cold. Every moment, the dunes are growing by an amount too small to measure, and the lakes are gathering a faint dusting of organic dust on their still surfaces. None of this is sudden. None of it would feel like motion if you stood there, but it never stops. If you could watch Titan from far away across many thousands of years, you might see the colors shift. You might see a hemisphere darken, then brighten. You might see the dune fields creep across the equator, grain by grain. You might see a methane lake slowly shrink as the climate drifts toward a drier age, or fill again as some hidden cycle returns. The moon is patient, its weather is patient, its chemistry is patient, and the haze keeps falling. Soft, golden, endless. A long, quiet snow of carbon, settling onto a world that has been painting itself in slow strokes for longer than we can easily hold in mind. What that painting will look like 1,000,000 years from now, no one yet knows. On a winter day in January of 2005, a small probe fell through the orange haze of Titan and sent back the only pictures we have ever taken from its surface. The probe was called Huygens. It was about the size of a kitchen table, and it carried instruments built to listen, to smell, to measure, and to see. It had ridden across the solar system tucked inside a larger spacecraft, waiting for this single, slow descent. When the moment came, it let go and it fell. The fall took about 2.5 hours. That is the strange thing about Titan. The air is so thick, and the gravity so gentle that even a heavy machine drifts down like a leaf in autumn. The parachutes opened in the high haze, and the probe began to drink in the light. What it saw at first was not much. A glowing orange fog in every direction, a muted sun, the world below hidden behind a curtain of organic mist. As it sank lower, the haze thinned. Shapes began to appear. Soft hills, dark plains, pale ridges, and what looked unmistakably like the branching arms of rivers. The light on Titan is not like the light on Earth. The sun there is about 100 times dimmer than the sun we know. The thick orange sky filters out the blue and the green, and what remains is a warm, dim glow, the colour of weak tea or a candle behind smoked glass. Noon on Titan would feel, to our eyes, like a long and gentle dusk. The pictures Huygens sent back have a haunting quality. They are grainy and pale, washed in soft amber. They show a plain scattered with rounded stones, smoothed as if by long tumbling in some ancient flow. The stones are not rock as we know rock. They are water ice, hard as granite in that cold, and they sit on a damp surface of darker grains. When the probe touched down, its instruments suggested the ground beneath it was soft, a little like wet sand, perhaps moistened by methane that had soaked into it long before. For about 90 minutes after landing, the probe kept talking. It measured the temperature of the air, the chemistry of the haze, the faint warmth of its own lamp reflecting off the ground. Then its batteries faded, and the signal grew thin, and the long silence of Titan closed back over it. Somewhere on that plain, the small machine still sits in the cold, slowly being dusted by Tholins drifting down from above. What Huygens taught us about light on Titan is still being studied. The probe carried a lamp, a small bright source meant to show the true colours of the surface without the orange filter of the sky. In its glow, the stones looked less like amber and more like dirty ice, streaked with darker organic stains. This hints that the warm colour of Titan, at least in the pictures we treasure, is mostly a trick of the air. Beneath the haze, the world may be paler, greyer, and more familiar than it first appears. Or it may not. The lamp only lit a small circle. The rest of the surface remains seen only through that orange veil. There are still open questions about what the descent images show. Some researchers think certain bright patches near the landing site may be exposed water ice, scrubbed clean by methane rain. Others think those patches could be deposits of a different chemistry entirely, perhaps frozen residues left behind when liquid evaporated. The shapes that look like dry riverbeds are widely accepted as river channels, but whether they flow often, rarely, or only during great storms is not yet settled. The light tells part of the story. The rest is guesswork. What lingers more than any single measurement is the feeling of those pictures. A pale world under a soft, dim sky. Stones rounded by liquid that is not water. A horizon that fades into haze rather than into distance. For a brief afternoon in the long Titanian year, a visitor from another planet opened its eye, looked around, and saw a place no human has ever seen with their own eyes, and perhaps never will. The light on Titan, then, is itself a kind of mystery. We have one set of photographs from one small patch of ground. The rest of that vast moon, with all its lakes and dunes and river valleys, remains lit only in our imagination, painted in the colours of an old map and a single dim afternoon. The probe is still there, asleep on the damp ground, waiting in the orange quiet for someone someday to come and find it. Sound on Titan would not behave the way it does on Earth. The air is thicker, the gravity is gentler, and the cold is deep enough to slow the dance of every molecule. A voice spoken into that orange atmosphere would carry farther and lower with a richer hum, almost as if the world itself were leaning closer to listen. And in that hush, scientists have begun to wonder whether something might already be listening back. Not in the way we picture aliens in stories, but in a quieter, stranger way. A second kind of life, perhaps, built from rules we have not yet learned to read. The thought begins with the lakes. On Earth, every living thing we know uses water as its inner sea. Cells are tiny bags of water, salt, and chemistry, and our whole story flows from that single fact. But Titan has no liquid water on its surface. It has methane and ethane, cold and clear, pooling in basins that look from orbit like dark mirrors. Some researchers ask a careful question. If life needs a liquid to mix its chemistry in, and Titan has rivers and seas of liquid, could a different kind of life have taken root there, using methane the way we use water? This is not a claim. It is an open question and a humble one. The chemistry would have to work in ways our biology does not. Cell walls on Earth are built from fatty layers that hold water in and keep methane out. In Titan's seas, that kind of wall would dissolve. So theorists have sketched a different kind of membrane, one made from nitrogen-rich molecules that could hold their shape in cold methane. They gave this imagined membrane a name and ran it through computer models, and found that, in principle, it might be stable. In principle, the molecules have never been seen forming on Titan. The idea remains a sketch on a page. Other researchers push back gently. They point out that chemistry slows almost to a crawl at Titan's temperatures, near -180 degrees Celsius. Reactions that take seconds on Earth might take centuries there. Life, if it exists, would tick at a pace we can barely imagine. A single thought, if such a thing applied, might unfold across a human lifetime. So even if something lives in those lakes, it might be too slow for us to notice in a brief visit. The mystery is not only whether life is there, it is whether we would recognize it if we found it. There are hints, too small to mean much on their own, that have kept the question alive. Some early models of Titan's atmosphere predicted certain gases should be present near the surface in measurable amounts. When spacecraft looked, those gases seemed scarcer than expected. One possibility is that something on the surface is consuming them, the way microbes on Earth consume oxygen or methane. Another possibility, just as likely, is that our models are simply incomplete, and the chemistry behaves in ways we have not yet captured. The data is thin, the argument is gentle. No one is claiming proof. If life does exist on Titan, the sounds of that world take on a different weight. The slow drip of methane rain on a frozen shore, the whisper of wind across a dune of dark sand. The soft lap of waves on the edge of a hydrocarbon sea. These would not just be the noises of a dead landscape. They would be the soundtrack of a living one, played at a tempo so slow it might sound to us like silence. The wind would carry molecules, the rain would carry chemistry, and somewhere perhaps something would be quietly making use of it all. We do not know. That is the honest answer. The Cassini mission saw enough to make the question serious, but not enough to settle it. Future missions may carry instruments designed to sniff for the kinds of molecules a methane-based biology might leave behind. Even then, the signals will be faint, and the interpretations difficult. A strange chemical pattern might mean life, or it might mean a quiet reaction no one has studied yet in a laboratory cold enough to match Titan's chill. For now, the lakes sit beneath their orange sky, dark and patient. The rivers carve their channels. The rain falls in slow, fat drops. And the question hangs in that thick air, neither answered nor closed. Somewhere on that distant moon, in pools we have only glimpsed from above, the universe may be running a second experiment in being alive. Or it may not. We do not yet know which silence we are listening to. Storms on Titan do not arrive the way they do on Earth. They build slowly in patterns that scientists are still trying to read. And yet, when you look closely at the numbers behind them, a kind of quiet beauty appears. The math of Titan's weather is gentle, slow, and surprisingly familiar. Titan circles Saturn once every 15 days and 22 hours. That number is fixed. We can predict it down to the second. The moon is locked to Saturn the way our own moon is locked to Earth, so one face always looks toward the ringed planet, and one face always looks away. This simple tidal lock shapes everything that follows. It sets the length of the days. It steadies the slow churn of the deep interior. It even guides the way the seas shift in their basins. Saturn itself takes about 29.5 Earth years to circle the Sun. That long orbit gives Titan its long seasons. Each season lasts roughly 7 Earth years. Spring takes 7 years to arrive. Summer takes 7 years to fade. The mathematics of that slow march means that a single storm season on Titan can stretch across what feels, to us, like an entire chapter of a human life. The distance from the Sun matters too. Titan sits about 9.5 times farther from the Sun than Earth does. The sunlight there is roughly 1% as strong as it is here. That small number explains the cold. It explains why methane can pool in lakes. It explains why the air is thick and patient, rather than fast and violent. The numbers set the stage, and the stage is quiet. The air pressure at Titan's surface is about 1.5 times the air pressure at sea level on Earth. That ratio is small, but it has enormous consequences. Combined with gravity only 1/7 of our own, the air feels dense and slow. A raindrop of liquid methane falls through that thick, low-gravity sky at perhaps 1 or 2 meters per second. On Earth, a raindrop falls about 9 meters per second, so a Titan raindrop drifts down nearly 5 times slower than ours. The math of falling rain becomes the math of falling snow. These raindrops are larger too. Some models suggest they may reach close to 1 centimeter across before they fall. They are big, soft, slow spheres of methane and ethane, sinking through orange haze. You could, in theory, watch a single drop travel for many seconds before it touched the ground. The numbers turn rain into something almost ceremonial. The clouds themselves form at heights of 15 to 30 kilometers, where temperatures hover near -180 degrees Celsius. At those temperatures, methane behaves the way water behaves in our own sky. It evaporates from the lakes. It rises, it cools, it condenses, it falls. The cycle has the same elegant shape as the water cycle on Earth, just shifted into a colder key. The same equations that describe a thunderstorm over a warm ocean here can be tuned, with different numbers, to describe a methane storm over Kraken Mare there. What remains open is how often these storms occur, and how strong they truly grow. Cassini watched giant cloud systems bloom over Titan's poles during certain seasons, then fade for years at a time. Some researchers wonder if the largest storms only arrive near the equinoxes, when sunlight shifts from one hemisphere to the other. Others suspect that powerful storms might happen more often, but in places the spacecraft simply did not see. The numbers we have are still too few to settle the question. There is also the slow mathematics of the seas themselves. Kraken Mare is roughly the size of all 5 of Earth's Great Lakes combined. Its tides, pulled by Saturn's gravity, may rise and fall by less than 1 meter, depending on where you stand on its shore. That gentle rhythm repeats every 15 days and 22 hours, matched to Titan's orbit. A tide so small on a sea so cold, moving so slowly that you would barely notice it from a boat. And yet it is there, every cycle like a slow heartbeat. Even the haze obeys numbers. The particles that paint the sky orange settle out of the upper atmosphere at rates measured in millimeters per year. Over 1 million years, they build a layer many meters thick. Whole landscapes are sculpted by that patient arithmetic. The mystery of Titan's storms is not chaos. It is a set of equations we have only begun to read, written in cold, in pressure, in tidal time. The numbers are simple. The picture they paint is still unfinished. In the south of Titan, the rivers run slowly. They wind across pale terrain in long, lazy curves, carving valleys into a crust of water ice that is harder than granite at these temperatures. The liquid inside them is not water. It is a cold mix of methane and ethane, flowing through channels that look from above almost exactly like the rivers of Earth. The shapes are familiar. The chemistry is alien. What makes these slow southern rivers possible is a balance so delicate it almost feels accidental. Titan sits at just the right distance from the sun, in just the right temperature range, with just the right atmosphere, for methane to exist in 3 states at once: solid, liquid, and gas. A few degrees warmer, and the methane would boil away into the sky and never return as rain. A few degrees cooler, and it would freeze hard into the ground and stay there. The window in which liquid methane can drift through the air, fall as rain, gather into rivers, and pool into lakes is narrow. Titan happens to sit inside it. Earth holds a similar gift with water. Our world hovers in a thin band of warmth where oceans stay liquid, where ice forms at the poles, where clouds carry rain across continents. Move our planet a little closer to the sun, and the oceans would simmer away. Move it a little farther, and they would lock into ice. The conditions that allow our rivers to flow are not guaranteed. They are a quiet accident of distance, atmosphere, and time. The Titan, in its own strange way, holds the same kind of accident. A different chemistry, a different temperature, but the same fragile arrangement. The slow rivers of the south flow because Titan's thick air slows everything down. The atmosphere there is denser than Earth's at the surface, and the gravity is weaker. Raindrops fall through this heavy air like feathers, drifting more than plunging. When they reach the ground, they gather without urgency. The methane rivers move at a gentle pace, shaped by gravity that pulls only about 1/7 as hard as ours. The whole system runs on a softer clock. If you changed one piece of this arrangement, the rest might unravel. If Titan's atmosphere were thinner, the methane would evaporate too quickly to gather into pools. If the air were thicker, the rain might never reach the ground. If the temperature swung even a little, the surface liquids would shift to gas or freeze to stone. The cycle depends on each piece holding its place. Researchers still wonder how stable this balance really is over the long span of Titan's history. Some models suggest the methane in the atmosphere is slowly being broken apart by sunlight, and that without some hidden source replenishing it, the rain could one day stop. Where that source might be, deep inside Titan, leaking from the crust, or something else entirely, remains an open question. The southern rivers are also shaped by seasons that last more than 7 Earth years each. As Titan circles the Sun alongside Saturn, the south slowly tips toward the light, then slowly tips away. Rain patterns shift. Lakes in the south appear to have shrunk over recent decades, while the northern lakes have stayed full. Why this asymmetry exists is still debated. One idea is that the orbit of Saturn itself, slightly stretched, gives the north longer, gentler summers and the south shorter, more intense ones. Another idea is that the underground plumbing of Titan favors the north, drawing liquid into hidden basins below the surface. The evidence so far is incomplete. What feels remarkable, lying in the dark and picturing it, is how easily this whole arrangement could not have existed. A moon orbiting a ringed giant, far from the warmth of the sun, somehow holding onto a thick nitrogen atmosphere for billions of years. Methane in just the right amount. Ethane gathering in lakes the size of inland seas. Rivers carving their slow paths through ice bedrock. None of it was inevitable. The same kind of quiet luck that gave Earth its oceans gave Titan its methane seas. The two worlds separated by nearly 1 billion miles, both running on the same trick of chemistry, sitting in the right place at the right temperature. The southern rivers keep flowing, slow and patient, through a landscape no human eye has ever directly seen. They do not know they are extraordinary. They simply move as rivers do under a pale orange sky, carrying their strange liquid toward basins that may grow or shrink depending on a balance we still do not fully understand. Somewhere in the next decade, a small craft with 8 rotors is meant to lift off from a launch pad on Earth and begin a long, quiet trip toward Titan. Its name is Dragonfly. It is built like a flying drone, only larger, sturdier, and dressed in instruments instead of cameras. When it arrives, it will not land once and stay still. It will hop from place to place across the dunes, settling for a while, then rising again, then drifting on Titan's thick orange air to a new patch of ground. No mission like this has ever flown on another world. The question that drives Dragonfly is simple to say and hard to answer. What kind of chemistry has Titan been doing all alone for billions of years? The surface is rich in carbon compounds. The air rains methane onto plains coated with Tholins, those dark sooty grains formed high in the haze. Water ice sits frozen as hard as rock beneath. When a comet strikes, or when warm water seeps up from below, those ingredients can mix. For a brief window, liquid water might touch organic molecules on the surface. What happens in that window, no one truly knows. One idea is that these brief warm puddles could push Titan's chemistry one small step further. The organic molecules might link into longer chains, the kind that on Earth sit at the base of biology. Some researchers wonder whether amino acids or molecules close to them could form in such places. A contrasting view says the windows are too short, the temperatures too unsteady, the mixing too gentle. The chemistry might begin and then freeze again, halfway through whatever it was trying to become. Dragonfly is built to look for either outcome, and to be honest about whichever it finds. The craft will carry a mass spectrometer, an instrument that sniffs samples and sorts their molecules by weight. It will drill a little into the surface, scoop up grains of dark sand and ice, and let the instrument read what is there. If the molecules are simple, that tells one story. If they are long and complex with patterns that hint at deeper chemistry, that tells another. The hope is not to find life. The hope is to find the steps that lead toward life. The rungs of a ladder Titan may have climbed partway up. There is a second open question Dragonfly hopes to touch. The Selk crater where it plans to land is a place where an ancient impact once melted the ice. For a short time in Titan's distant past, a pool of liquid water sat there, mixing with the organics that coat the surface. That pool is long frozen now. The question is whether it left a record. The frozen ground beneath Selk might hold preserved molecules from that brief warm chapter, like pages pressed inside a closed book. If those pages can be read, they will tell us what kind of chemistry actually happened, not just what we guessed. The mission also carries questions about Titan's air. Why is so much methane in the atmosphere when sunlight should slowly destroy it? Something must be refilling it. One theory points to cryovolcanoes, those slow, icy vents that may release methane from below. Another points to the deep ocean of liquid water sealed under the crust, leaking gas upward through cracks over long ages. A third possibility is simpler still, that Titan is now spending down a reservoir laid down long ago, and the methane will, in time, run out. Dragonfly will not solve this on its own, but each measurement it makes will narrow the choices. The most patient question is the one no instrument can answer in a single visit. If Titan's chemistry has been running for 4 billion years in cold, dark, slow conditions, what has it built? On Earth, life appeared within the first billion years in warm water. Titan offers a different recipe, with liquid methane on the outside and liquid water hidden far below. Maybe nothing has stirred in either place. Maybe both places have stirred in ways we have no language for yet. The honest answer is that we do not know, and we will not know from Dragonfly alone. What this mission offers is a first close look at a working chemistry lab the size of a moon, one that has been quietly stirring its ingredients while we were still learning to walk upright. Dragonfly will not finish the story. It will only open the first real chapter, hopping from dune to dune, listening to the soft orange wind, taking small samples of a world that has been preparing them in the dark for longer than our planet has had a sky. Titan's surface, as we see it now, is split between bright hills and shadowed basins. The pale highlands rise softly, pale as old bone under the orange haze. The dark lowlands gather the organic sand, the sluggish rivers, the slow seas of methane and ethane. From orbit, the contrast looks almost painted, like watercolor washed across a frozen world. The question worth sitting with tonight is what this scenery will look like far in the future, long after our own lives have passed. 1,000,000 years from now, Titan may look much the same to a casual eye. The seasons will have turned many times over, each one stretching across about 7.5 Earth years. Rain will still fall in slow, heavy drops. Dunes will still creep across the equator, grain by grain, but small things will have changed. A coastline may have shifted by a kilometre. A river channel may have cut a little deeper into the ice. An island in Ligeia Mare may have grown, or vanished, or returned in a different shape. 100 million years from now, the picture grows harder to predict. Titan's methane is slowly broken apart by sunlight high in the atmosphere. Each broken molecule drifts down as heavier organic dust, settling onto the surface like a soft, endless snow. Some researchers wonder whether the methane in the air and seas might run out entirely on long timescales, unless something deep inside the moon keeps releasing fresh supplies. If the methane fades, the rain may fade with it. The seas could shrink. The clouds could thin. The orange haze itself might pale, and the sky might clear in ways it has not in a very long time. But another possibility stays open. If cryovolcanoes do exist on Titan, and if they vent methane from a hidden reservoir below the crust, then the cycle could refresh itself again and again. The seas would persist. The rain would keep falling. The dunes would keep marching. We do not yet know which path Titan will follow. The answer waits inside the moon, locked beneath kilometers of ice we have not yet drilled through. 1 billion years from now, the sun itself begins to change. Slowly, gently, it grows brighter. Its outer layers swell. The inner planets will feel this first, their oceans evaporating, their skies thinning. But out at Saturn, the warming arrives more gradually. Titan, frozen for so long, would begin to feel a new kind of light. The methane seas might boil away into the sky. The water ice that forms the bedrock might soften. Some researchers have suggested that, for a brief stretch of cosmic time, Titan could become a temperate world, with liquid water on its surface and a thicker, warmer atmosphere. Whether life could take hold in that warmer window remains an open question. The window itself may last only a few 100 million years, which is short by cosmic standards and very long by human ones. Then in time the sun will swell further still. It will become a red giant, and its outer layers will reach far past where Earth once orbited. Saturn and its moons will be bathed in a kind of light they have never known. Titan's seas, whatever remains of them, will likely be gone. The pale hills may glow under a vast red sky. The shadowed basins may fill with new chemistry no one has ever modelled in detail. After that, the sun will shed its outer layers and settle into a small white ember, cooling slowly across billions more years. And here is where Titan's far future becomes almost unimaginable. The white ember of our sun will give off less and less warmth. The outer solar system will grow colder than it has ever been. Titan's atmosphere, if any remains, might freeze and fall as a final, gentle snow onto the surface. The moon would become a dark sculpture of ice and frozen air, drifting around the dim coal of a dead star. The bright hills and shadowed basins might still be there, recognizable in shape if anyone were left to look. What the universe does with these long stretches of time is not destruction so much as transformation. Worlds do not simply end. They become something else. A methane sea becomes an organic sediment. An organic sediment becomes, perhaps, the chemistry of a future world we cannot yet picture. Titan, in every version of its future, keeps moving through change at its own slow pace. We will not see most of this. The question of what Titan becomes belongs to time itself. For tonight, the bright hills and shadowed basins are enough to hold in mind, quietly, as the orange sky drifts above them. Step back now, far enough to see Titan as a single pale point in the dark. From this distance, the lakes vanish, the dunes vanish. The orange haze becomes a soft glow no larger than a grain of sand held at arm's length. And yet inside that grain, rain is falling. Rivers are flowing. A sea the size of a small ocean laps at frozen shores under a sky no human eye has ever seen in person. Somewhere beneath that surface, hidden under many miles of ice, there may be a second ocean. Not methane this time, but water. Salty water, perhaps warmed by the slow squeeze of Saturn's gravity. The evidence is gentle but real. Titan's shape shifts a little as it orbits, and that shifting hints at a soft layer deep inside. Some researchers think this buried ocean could be larger than all the lakes on the surface combined. Others wonder how thick the ice above it really is, and whether anything from the surface could ever sink down to meet it. If that hidden ocean exists, Titan becomes something stranger still. A world with two kinds of seas, one of methane open to the orange sky, one of water sealed in darkness, two liquids that never touch, separated by a shell of ice. The question of what moves between them, if anything moves at all, remains open. Pull back further. Saturn glows nearby, its rings catching the distant sun. Titan is one small light among many moons, and Saturn is one small light among many planets, and the Sun is one small light among hundreds of billions in our galaxy. The galaxy itself is one among trillions, and somewhere in all that vastness the same atoms keep showing up. Carbon, hydrogen, nitrogen, oxygen, the simple letters from which everything is written. Those atoms did not begin here. They were forged inside stars that lived and died long before the Sun was born. The carbon in Titan's methane, the carbon in the dark dunes, the carbon in the haze above, all of it was cooked in the cores of ancient stars. When those stars ended, they scattered their atoms across the dark. Some of those atoms drifted together into the cloud that became our solar system. Some became Saturn, some became Titan, some became the body listening to this voice right now. The calcium in your bones came from exploding stars. The iron in your blood came from the same kind of furnace. And the carbon that builds every cell in your body is the same carbon that falls as rain on Titan tonight. We are not separate from these distant worlds. We are made of the same scattered ash. That is part of why Titan feels so strange and so familiar at the same time. The chemistry is alien, but the elements are not. The rain is not water, but it is still rain. The rivers are not warm, but they still carve valleys. The seas are not blue, but they still hold tides. Saturn pulls on Titan, and Titan pulls back, and the cycle repeats as it has for billions of years. If life of some kind does exist there in the methane lakes or in the hidden water below, it would be a quiet cousin of life on Earth. Made of the same starlight ash, shaped by the same physics. Solving the same problem of how to gather energy in a cold and patient universe. Whether that cousin exists, no one knows. The question may not be answered in our lifetime. It may not be answered for many lifetimes after ours. And that is all right. Some mysteries are meant to be carried, not solved. Some questions are gifts. They keep the imagination warm on long nights. They remind us that the universe is not finished telling its story, and that we are part of the telling simply by wondering. Titan turns slowly on its axis, taking 16 Earth days to complete a single day of its own. The haze drifts. The methane gathers into clouds. Somewhere a soft rain begins to fall on a dark dune, and the grains shift, and a small channel deepens by a fraction of a hair. The hidden ocean below sloshes gently against its ceiling of ice. The seasons inch forward. Saturn rises and sets in a sky no one is watching. We share atoms with that distant rain. We share a sun and a galaxy and a long, quiet history reaching back to the first stars. Out there beneath an orange sky, a world is doing what worlds do. And here beneath a different sky, you are doing what bodies do. Resting, breathing, belonging to the same wide, unfinished universe. And so we come to the quiet end of our slow walk across Titan. We have stood beneath an orange sky. We have watched methane rain fall in slow, soft drops. We have traced rivers that carry no water and listened in our imagination to the wind moving over dark dunes of frozen soot. There is nothing more to learn tonight. There is only the gentle drift toward sleep. Picture Titan now, turning slowly in the deep dark beyond Saturn. Its haze glows like a soft lantern, a small warm bead suspended in the cold. The rings of Saturn shine somewhere above its thick clouds, though the surface never sees them clearly. The light there is dim and amber, like the last light of an old evening on Earth. Nothing on Titan is in a hurry. Nothing has ever been in a hurry. The seasons take decades. The rain takes years. The lakes lie still beneath skies that change so slowly they seem painted in place. Imagine standing on a quiet shore of Ligeia, Mare. The liquid methane is calm, smooth as dark glass. Small ripples move across it, slower than ripples on any pond you have ever known. The gravity is gentle. Your steps would feel soft, almost floating. The air would press against you thick and steady like warm water that you could breathe. Above, the haze hides the stars. You would not see them. But you would feel the size of the sky all the same. We do not know yet what truly lies beneath that calm surface. We do not know what kind of slow chemistry stirs in the cold. We do not know if some quiet form of life, built from parts we have not yet imagined, drifts through that liquid in patterns we cannot guess. The question stays open, and that is all right. Some mysteries are not meant to be solved tonight. Some are meant to be held gently, while the mind grows soft and the body grows still. Far below the methane seas, an ocean of salty water may rest in darkness, warmed by the slow heat of the moon itself. It has been there perhaps for billions of years. It may hold answers. It may hold nothing at all. The ice above it keeps its secrets well. We can listen for clues, but the ocean does not speak quickly. It speaks in tides, in faint shifts, in the soft pull of gravity over long, long time. And around Titan, the wider universe turns. The Milky Way wheels slowly in its great spiral, carrying our Sun, our Earth, and all of Saturn's family along with it. Other galaxies drift in the dark, each one a small soft glow in the deep. None of them are rushing, none of them are anxious. They simply move as they have always moved in the long, slow rhythm that holds everything together. You are part of that rhythm too, your breath slowing now, your shoulders soft against the pillow, the small quiet pulse at your wrist. You belong to the same universe that wraps itself around Titan, that warms the hidden ocean, that paints the haze in orange light. You are not separate from it. You are a small, warm, breathing piece of it, resting in your own quiet corner of the dark. There is no need to remember any of what we spoke about tonight. The dunes will still be there tomorrow. The rivers will still wander. Kraken Mare will still lie under its soft sky, waiting. The mystery of Titan is patient. It has waited for billions of years already. It will wait a little longer while you sleep. Let your thoughts grow slow now. Let the orange sky settle behind your eyes. Hear, if you like, the faint hush of a methane breeze moving over a frozen plain. Feel the gentle weight of a world far away, turning kindly in the dark. The universe is vast. It is also, in its own strange way, gentle. It holds Titan. It holds Saturn. It holds the long, quiet ocean beneath the ice. And it holds you here in this small, soft moment before sleep. Rest now. The questions will still be here when you wake. The wonder will still be here. The pale orange moon will still drift beyond Saturn, keeping its quiet secrets under its thick golden haze. There is nothing more you need to do tonight. There is nothing more to know. There is only the slow turn of a faraway world, and the slow, soft turn of your own breath settling into sleep. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.